Every Saga tutorial shows the happy path. Nobody shows what happens when the refund fails too. You've shipped this shape before. Charged the card, reserved the seat, sent the confirmation. 3 services, 3 separate transactions, nothing underneath holding them together at once. Because when the last step breaks, you don't get 1 rollback for the first 2. You get 2 brand new operations run in reverse, betting the world hasn't moved on yet. August 2012. A bad deploy leaves 1 server at Knight Capital running old, repurposed trading logic. 45 minutes later, it's fired 4 million trades nobody wanted. $7 billion of stock the firm never meant to own. $440 million gone. There was no undo button for that. Knight didn't roll anything back. Engineers spent the next 2 days on the phone, manually unwinding trades with other banks. The firm barely survived the week. Teams assume that failure story is rare, but it's not a crash you'd notice. It's money and orders sitting in an ambiguous state between 2 systems that each think they're right. Nobody pages you for that. It just sits there, technically fine, actually wrong. A typical checkout today touches 3, 4, sometimes 5 separate services. Inventory, payment, fulfillment, notifications, each one commits on its own clock. None of them has ever heard of the others. You don't run a trading floor, but the shape's identical. Any system with more than 1 service and 1 shared outcome is 1 bad network blip from that same problem. Just swap in your customers' money instead of Knight Capital's. Inside 1 database, this is already solved. You wrap the write in a transaction, begin, update the account, update the ledger, commit. Fail halfway and the whole thing unwinds automatically. That's the deal every backend engineer has taken for granted since the day they learned SQL. Now split that write across 2 services. Payment has its own database. Inventory has its own database. No shared transaction log. No shared log table. Nothing spans both. Picture an order service and a payment service, each with its own Postgres instance, each perfectly correct on its own. Nobody notices right away because most requests never touch the seam. Draw that second box and the guarantee you were leaning on quietly disappears. So engineers reach for the obvious fix. Make the commit itself distributed. A coordinator asks every service to prepare and collects a vote from each one. It only signals commit once every vote is yes. On paper, that's the same atomic guarantee, just stretched across a network. That coordinator is usually a real separate piece of infrastructure. Sometimes it's literally called a transaction manager, sitting between the databases and everyone's application code. This is 2-phase commit formalized in the XA specification back in 1991. That's 4 years after the Saga pattern was even published. Big banks and application servers adopted it all through the 90s for exactly this reason. It made a distributed system look from the outside like a single database. And it works. Every participant locks its rows, waits for the signal and commits together. From the outside, 2 services just behaved like one. Looks closed, it isn't, and the failure mode waiting underneath has nothing to do with anyone's code. It's baked into the protocol itself. Here's the failure everyone skips in the diagram. The coordinator collects every yes vote. Then, before it can broadcast the final commit, it crashes. Maybe the process dies, maybe the network partitions. Doesn't matter which. What matters is what every participant is holding at that exact moment. Every service that voted yes already promised to commit if asked. It can't safely abort. The others might have committed already. It can't safely commit on its own either. It might be the only one. So it does the only safe thing. It holds its locks and waits for a coordinator that may never come back. Distributed systems people call this the blocking problem. It's been known since the 1980s, and it's the whole reason 2-phase commit never became the default. Not once services stopped sharing one team and one database. This is a structural property of the protocol, not some rare edge case. Gregor Hopp put it best. Using 2-phase commit at your local coffee shop would kill the business. The line stops moving the moment one order gets stuck. So almost nobody runs distributed 2-phase commit across services they don't fully control. What they run instead is a Saga. a chain of ordinary local transactions, each one committing on its own, each one telling the next service to go. It reserves the inventory, charges the cart, then hands off to shipping. 3 separate commits, 3 separate databases. No coordinator holding a global lock across any of them. When every step succeeds, it's fast and it looks exactly like one transaction. Then shipping fails. Maybe the warehouse is empty, maybe the carrier rejects the label, doesn't matter which, the cart's already charged, the inventory is already reserved. There's no commit log to roll back because there was never one transaction to begin with, just 3 independent decisions, 2 of them already final. The instinct is to treat this as undo, running in reverse. That's not what happens. A refund is a brand new request to the same payment provider over the same flaky network. It can time out, it can get rate limited. It can fail for a reason that has nothing to do with why the original charge succeeded. Compensating a transaction means running another transaction. It inherits every way the first one could fail. So when a saga fails, it walks back down the chain it already committed. For each completed step, it runs one of these new operations. Release the inventory, refund the cart. Each one is its own transaction with its own chance to fail. And when the compensation itself fails, you're not back where you started. You're in a third state nobody designed for. Charged, not shipped, now not refunded either. That state never shows up in the happy path diagram. Which means every compensating action needs the same idempotency discipline as a payment retry. If a timeout sends that refund call twice, it has to be safe to run twice, not double the refund. This is why compensations have to be designed, not assumed. Which steps actually need undoing, in what order, and what happens when one of them needs retrying. None of it comes free the way a database's own rollback does. In practice, teams write this down explicitly, often as a state machine, something like a step function's workflow. Each step names its own compensation in a catch block. The platform walks the chain in reverse the moment one step reports failure. Frameworks like Temporal or AWS step functions exist just to make that state machine durable, so it survives the same kind of crash that took down our coordinator back in two-phase commit. Some teams skip the central coordinator entirely and do this by event. Each service publishes what it did, listens for what came before it, and decides on its own whether to compensate. No orchestrator, no single point of failure. But now, the compensation logic is scattered across every service instead of written down in one place. Netflix built its own version of this called Conductor. It coordinates hundreds of these chains across teams that don't share a database, a queue, or even a deploy schedule. This isn't theoretical. Chris Richardson literally wrote the book on this pattern. He maintains an open source reference implementation of exactly this saga. There's a filed bug against it. When a later step fails, only one of the 2 expected compensations actually runs. The order ends up cancelled instead of rejected. Small bug, teaching example, not a trading flaw. Same missing piece. You won't find a company blog post titled "Our Saga's compensation failed." Nobody writes that up. It gets fixed quietly on call at 2 in the morning. The post-mortem never uses the word saga at all, which probably means every team that shipped one of these has hit some version of this, they just never had a name for it. Scale that same missing undo button up to a trading floor. You get 45 minutes, $440 million. The mechanism's the same, size just decides how loud the post-mortem gets, or whether it gets written at all. None of this means don't build the saga. It means stop treating the compensation like an afterthought, when it's doing the hardest job in the whole system. Two-phase commit isn't dead everywhere. Google Spanner runs it across shards it fully controls, where every participant is itself replicated, so losing one coordinator doesn't freeze the world. Google's earlier Percolator system did the same thing across Bigtable for its search index, entirely inside infrastructure Google alone operated. CockroachDB does something similar inside a single cluster. The pattern works when one team owns every failure domain end-to-end. Nobody outside that boundary can crash your coordinator. CockroachDB's own engineering team measured what collapsing that protocol down to one round trip does. It changes commit latency across a cluster, roughly cuts it in half. Inside one system, atomicity is still worth chasing hard. So here's the actual decision rule. If you own both sides and control how they fail, reach for a real atomic commit. The moment a request crosses a team boundary, a vendor boundary, or a deploy you don't control, stop pretending. You won't get a rollback. Design the compensation like a first-class feature instead. This is an org chart decision more than a technology one, and most teams get it backwards. That means giving every compensating action its own idempotency key, its own retries, its own alert too for when it fails twice in a row. Treat refund didn't go through as an incident, the same way you treat charge didn't go through. Right now, most teams only monitor one direction. That's the gap this whole video has been about, and it's the cheapest fix in it. SAG isn't. A Saga was never an undo button. It never had a rollback to give you. Every compensating action is a brand new transaction. It places a brand new bet that the world holds still long enough for it to land. That's the whole trick, that's the whole risk. And it's exactly what the happy path diagram never shows you. Compensating transactions aren't rollbacks. They are new bets on a world that already moved on. So next time Saga promises to undo a fail step cleanly, stop. Ask what happens when the undo step fails too. Now you know the answer, and now you know what to build for it.